Hello, everybody. Welcome. Everything's going to be in English, as you realize, because we not only have guests that attend the meeting in person, but also from the web link that is available for Patras IQ, but also because it's recorded and it's going to be part of the documents and information that we're going to include in the final package of the project. So, excuse my so-and-so English, and let's move on. Why you are here? Sunsets, which is the short name of the project's name, which is Modular Control Systems for Maximizing Solar Energy Utilization and Grid Service Provision by Residential PV Systems coupled with Thermal Storage, is a long name. For practically what we're doing is we try to create technologies for local energy communities. Each partner of the project, I will make a detailed presentation of the partners and everything later on, but until everyone joins from the online space and everything is settled, I would like to say that it's a very wide range of technologies that have been developed. You will see some of them, some significant ones, and you will only see a few people that present and show you what has been done. There's a lot of people working behind the scenes, endless hours of spent on their work, and many details that took a lot of effort and a lot of patience in order to be overcome. So don't stick that this is the project. The project is far... Okay, cheers. So, most of you have already registered for this workshop here. In case someone just walked in or he was not informed in advance about it, I will show you a QR code now, which practically you have to scan now. I don't see the people from the online, they have already registered, they don't see it. Whoever is in the room and wants to register, I would advise him to register, has to scan. Can you please, βγάζετε λίγο το κωδικό QR σας παρακαλώ στην οθόνη, στο projector. Το QR. Που θα βγει τώρα στην οθόνη, αυτό, το σκανάρετε, you scan it, and you register, and some very basic information about who you are, because we're interested in the statistics and the numbers, will be registered so we know what are you, if you're a student, if you are an academic, if you are some investor or whoever is interested on that. And maybe there will be follow-up communication about where you can check the presentations, where you can check some more information about the project. More information is in the web page we have, which is sunset.upatras.gr, and it will be updated as soon as we go through the final stage of certification as a project, which means by the end of the year, this has to be done. So that's the QR code you probably, if you have registered already, you don't have to do it again, okay, it's clear. Now, let's move on to the presentation side. Our first speaker, Georgios, is replacing the head of the department, Professor Alexandridis, because he had to go to Athens for some significant obligation he had, so he will not be able to attend. Georgios is in the same lab, Georgios Konstantopoulos is in the same lab with me, and he will present to you the main research activities of the lab and who we are. The University of Patras is the coordinator. Most of you are in the University of Patras one way or the other. So I think it would be nice to have a very short presentation of what we're doing beyond the project and with the project included. So I would like to invite Associate Professor Georgios Konstantopoulos to take up the presentation. Okay. Thank you, Georgios. Κάτσε να σου βάλω το...
Thank you, Panagis. Good afternoon, everyone, and welcome to this workshop. So unfortunately, Professor Alexandridis couldn't make it, so I had to step in and just give a short, very short presentation on our research team and our activities. So we are, our laboratory, our research laboratory is called Power Systems Renewable and Distributed Generation Laboratory. Let's see if it moves. All right, so this is who we are. So the head of the lab, and currently the head of the department is Professor Alexandridis, and then myself with my colleagues, Dr. Vovos and Dr. Patras are the academics. We currently have 2 postdoctoral researchers and 7 PhD students, so we are continuously expanding and continuously recruiting students who would like to pursue this kind of research. So our focus includes these following key parts that start from the developments of the renewable energy resources and their control design, their interface devices, so we're talking about the design of the converters and their integration with the grid. But moving up, we look at the modern power system as a cyber-physical architecture, so we target several challenges that, let's say, appear when we look at it from a cyber-physical point of view. In terms of control, anyway, I'll use the mouse if it appears here. Okay. So we do some dynamic analysis and control design of different levels of the hierarchical structure, from microgrids to large-scale power networks. And also, we look at the modeling, the analysis, and the design of wholesale, retail, and local electricity markets as well. So finally, I will show you a few slides of each one of those research activities, and finally I will present some key elements that we have, let's say, experimental setups that we have in our lab that help us validate, let's say, the proposed approaches. So from a cyber-physical point of view, if we look at the modern power grid architecture, so we've got the physical layer that includes the, let's say, energy resources, the loads, the network. I'm talking about the electrical network, along with the market layer and the societal layer as well. And then the cyber part, let's say, of the network, whatever you see inside the blue dust lines. Okay, so we're talking about the monitoring, data processing, communication, and then decision-making that occurs at different levels, from supervisory control of these devices to the network, to economic operation optimization, and even energy planning. So this is the big, let's say, image. We're trying to target, the majority of those challenges from the devices, right, from the bottom and the physical layer to their control, to the supervisory operation, energy markets, and also how we close the loop with the cyber part. Okay. So a lot of work that we have done is on let's say, a lot of theoretical work on power networks. So we're talking about dynamic stability and modeling of large-scale power systems. On the right, you see this kind of cyber-physical architecture I was talking about. So this is the physical plant, our network, right, the power system, and then the cyber part, which is the monitoring, control, and communication part. And we are trying to investigate the challenges that occur from different disturbances, either at the physical system, physical disturbances. It could be tie outages, sudden disconnection of renewable energy resources or key, let's say, generators in the network, but even also disturbance in the cyber part, which is cyber attacks, loss of communication, and so on. This is one example of the modeling approach that we have created that describes also the nonlinear phenomena inside the power network and how we can model it in a, let's say, a nice structured way that allows us to do this, the control technologies and the stability analysis afterwards. Now, since we talk about the cyber-physical part, so a key aspect and a hot topic nowadays is how to investigate the energy markets. So we've got, our colleague, Dr. Papadaskalopoulos will also have a presentation about it this afternoon, so I won't say too much here. But we look at it from the modeling, the analysis, and design, not only of the wholesale markets, but also of retail and local energy markets that include also peer-to-peer energy trading for the modern communities. And just going now down from the, let's say, the big power network towards more local and distributed distribution networks. So in terms of the distribution network, we do a lot of work in the microgrids part, so small-scale power networks that are islanded or connected to the main grid, and how we can control the individual units, and then multiple units within a microgrid and multiple microgrids within a distribution system. Right? So all these different levels of the hierarchical control, starting from the bottom, right, the primary control of the units, towards the supervisor control part. And again, going now to the devices. For its renewable energy resources, we focus also on the design of the interface device, the converters that integrate them with the grid, and also their controller and the interaction with the grid, right? So when you have a weak grid, it can have variations in the voltage, frequency, and so on. How can this, we can support it from our individual units. So these are some of the equipment that we have in the lab, right? A solar roof, a PV solar that we have at the rooftop, a small wind turbine, and a couple of other flexible loads and generations in our lab to form a microgrid that we can monitor in real time. So I will conclude this presentation just by showing you the key lab facilities. Some of them were shown in the previous slide. So currently, we have several of real-time digital simulator units. These are what you see here with this black one, devices here from Typhoon Hill. So that helps us perform real-time simulations of large-scale power networks, but also hardware-in-the-loop implementation of energy resources, right, and small microgrids. We have several controllable power converters that are very flexible, so we can apply different control strategies and test them in the lab. A few motors and generators. So if we want to focus on the, let's say, emulation of, let's say the experimental implementation of motors like in electric vehicles or in wind generation systems, that we have this kind of real motors that can be controlled through these controllable inverter devices. And finally, that microgrid I was talking about. So we've got this PV. Currently, we're placing an EV charger in our let's say, parking garage, let's say, of the department. So we can also monitor that. The small wind turbine that we have, plus fuel cell and a few battery emulators. So we can combine them together and form a real microgrid inside our lab that we can monitor and do several things, from the integration of units, like the control of the individual units, but also the management of the multiple generations altogether. I hope I just gave you a brief introduction of our lab. Again, we will be around, so if anybody has any questions, please feel free to just get us in the hallway and discuss more about it. Right. Thank you.
Thank you, Georgios. I don't know if there's any questions from the people attending here or from away. Okay. I'm glad there are no questions since everything is clear, and we can move on to the next presentation. Thank you, Georgios. Okay, so the next presentation is going to be my work. The University of Patras was the coordinator of the project, so my target is in the next 10 minutes to give you an idea of what was the project about in general. And then the presenters that will follow will give you more details about specific parts of the project. So I have explained in the beginning of this workshop that the point of this research project was the modular control systems for the maximization of solar energy utilization and grid service provisions by residential PV systems coupled with thermal storage. So what is Sunsets about? First of all, it's a Solar Eranet Co-Fund 2 program, which means it's approved by the European Council, but it's funded by local agencies around Europe. The call of the project was to focus on operation and system integration of PV plants, and specifically, the system integration should be improved via ancillary services which assure a stable grid in spite of fluctuations of demand and generation, which is a very significant difference of traditional power systems. The Sunsets performed research and development of new technologies aiming at making advantages out of traditional disadvantages of highly PV-dominated systems that involved a high penetration of nearly zero energy buildings, which are the foundation of a theoretical or existing somewhere local energy community. The nearly zero energy building, which we demonstrated before, is the core, and on that we build on greater clusters, which are controlled in a better way. The technologies aimed on two things. First of all, to improve the ability of a local distribution system to absorb more PV generation. As we know, even existing grids face a great problem with absorbing more PV power because the grid cannot support that, or the technology in place cannot support it. And secondly, we want to, with the technologies provided, to improve the efficiency of the local energy community. For those who are not connected with local energy communities, they're communities that group users of, consumers of energy, but producers of energy together in a group so that they can improve, first of all, the financial income from sold energy, but also improve the expenses, reduce the expenses of energy bought from the grid. So it's actually something like working together so we'll get better prices. That's the main target. But at the same time, exactly because we want to improve that, you get technologies that allow you to improve the stability and the flexibility of the services and the grid that is in place for the local energy community. So the way Sunsets see a nearly zero energy building-based local energy community is divided in three layers. On the physical layer, you have the actual infrastructure of the local energy community, which involves nearly zero energy buildings as main molecules in the process, together with local generation, and assuming that you have an electricity grid which has great capacity in terms of new technologies in order to monitor, sensor, and process commands from a central or distributed command center, you can get, you can manipulate the way your local energy community operates. That's the physical layer. On top of that, we have the IoT layer, which is the Internet of Things layer, where all the data is collected, processed, and decisions are taken so that these resources are optimized. There is some clustering take place, which divides these cloud, let's say, in smaller clusters that is easily controllable and commands are more clear, and the infrastructure and workload on this higher level is reduced. And this allows to develop technologies out of the same equipment in place, out of the same physical layer. On top of that, you have the application layer, which you use by manipulating your resources, your cluster resources in the IoT layer, in order to provide, as a whole, as a community, flexibility of your consumption and generation to the grid. In other words, you provide the service to the grid operator for an income or a better price as a compensation. You also provide better services on your own grid in order to keep it more stable and more and better quality of supply. So at the end of the day, it's not all about economy, but also of quality of supply and reliability of supply. So that's more or less the way the hierarchy that was followed by our project. Now, coming down to the core molecule of the project, which is the nearly zero energy building. It's a building that tries to have a zero emission footprint at the end. In other words, as a total at the end of the year, the whole energy must come more or less completely from the production that is in place on top of the building. So what we have here, we have energy produced by the photovoltaics, but also from traditional solar panels, which are quite common here in Greece. This produces electric power, but also thermal energy in terms of the water. This comes into the closed system, which is called the nearly zero energy building, and is controlled by a building energy management system. On top of that, to make our building as autonomous and as close to zero as possible, we have storage devices. In this case, we used the technology which comes from Sweden and from Ancillary, which is thermal storage based on aluminum materials which absorb electric power and convert it to heat, which is stored into a well-insulated box, let's say. And then from this stored heat, you can take back either thermal power directly or electric power from a Stirling engine that can also recover some losses from that and get a very high efficiency. Also, in this project, we utilize some quite neglected storage devices that we all have at home. And these storage devices are the boilers, either the solar boilers on the rooftop or the simple electric boilers on the bottom. We use the energy transfer to that, not only to store energy for later use, because as you know, these boxes are well insulated as well, but also while we produce this thermal power to give additional services to the electric grid. And I will talk about it in a later presentation in more detail, so you will understand exactly what I mean. So the point is to have a nearly zero energy building that not only provides what it says, nearly zero energy as a whole, but also provides services to the power grid with the storage in place. Now, the way we approach the subject is broken down into three interconnected clusters. First of all, our vision was to create a resilient distribution grid which has increased PV penetration without compromising the efficiency. The second bit that is interconnected with that is the proof of concept. We wanted to demonstrate with actual equipment in place and demo sites that we have created technologies that are optimal for the local energy community operation and which have a high PV penetration. So we didn't stick only to the vision, but we have proven with our demonstration sites that it works well. And this is an interconnected cluster with a demonstration, evaluation, and exploitation path, because not only we demonstrated the proof of concept, but we created a whole demonstration site Some demonstration sites are in Sweden, some demonstration sites are in Greece, and we also have created a virtual interconnected demo site that virtually connects two demo sites, one in Sweden and one in Greece, in order to show the full, in order to do the full evaluation of these technologies. And on top of that, we have created financial tools to see what actually you can make out of it, to monetize it, to get maximum value out of it, even from variable prices in place. Επειδή υπάρχουν και ξένοι και πάρα πολύ γι' αυτό. Να είστε κάτω. Υπάρχουν και ξένοι στο παραγωγή.
Ζήτησα μήπως έχει μια μετάφραση.
Εάν θέλετε να περιμένετε στο τέλος, θα σας τα πω όλα.
Καλά, δεν σας έχει. Ευχαριστώ.
Να είστε καλά.
Στο site.
Να είστε καλά. Να είστε καλά. So, coming to the implementation, we'll just give you some very short information of how it was done. We broke it down in 7 work packages, which break down to management and dissemination, design of the whole technology infrastructure and the technology involved, and demonstration and exploitation. As you see, one cannot go without the other. For this, more than 100 months of work have been involved. The whole project had a budget of 750,000 euros, which break down to, which also involved 100,000 euros coming from self-funded activities. The proportion of money spent from the academic partners and the industrial partners was about 3-to-1. So it is quite academic research work done, but at the same time, quite a push was given to the industrial partners to participate and give as much as they could. The Swedish budget was about 500,000 euros, and the Greek partners had about half of this number. Now, coming to the roles of the partners, what each one of us did, each partner did, fortunately, I have to present the University of Patras first because it was a coordinator, and many of you are involved in this institution. 4 staff was involved, 4 members of staff. Some of them were researchers, some of them were PhD students, and I was the academic supervisor of the overall project. We had to take care of the coordination and do the operating analysis of what I called before smart boilers. First through simulation, and then via the controller, the development of the controller of the smart boiler. We also created a demonstration site for the suggested system in Greece, in place in the University of Patras, which you are welcome to attend and see how it works. We were also responsible for the dissemination of the results, and this includes website, some seminars, our place here, and so on. Now, moving on to the second partner, academic partner, we have the University of the Peloponnese, which involved 3 members of staff, and they worked mostly on the hardware required by a boiler to become smart. And this had we had a lot of interaction with them because we developed that together. As you know, simulation, implementation, and result doesn't come separately. You have to reiterate between these 3 stages. And they also worked on the forecasting of the effects of the energy variability and generally did the financial analysis of our attempt here. Also, they worked on the forecast of the economic impact of the proposed system developed by sunsets, not only about the smart boilers, of course. And I move on now to our Swedish academic partners, which is Chalmers from Gothenburg, and 5 people were involved from there. And they focused most on services that support the grid, and they provide flexibility to the system, and facilitate the large integration of photovoltaics in the system. They created some innovative tools for improved energy community efficiency, and that included also Azilios, the Swedish industrial partner technology, storage technology. They provided grid supporting and flexibility services to grid operators as well. And they have created an allocation mechanism for fair compensation of the resources that provide those services. Now, they also created demonstration sites in Chalmers campus, and there was also a demonstration site in Asilio. I will tell you more about this later. Now, coming to the industrial partners, there was Maltezos. You probably heard this company that provides boilers to the Greek market and abroad. A member of the staff, the chief engineer, was involved, and he's present here, and he will give you a speech later on. But also, I believe there was a lot of work done behind that, because they provide us a lot of equipment and expertise of the thermal part of the system. Now, they assisted to the creation of the thermal part, as I mentioned, and they designed and provided equipment for the creation of the demo site in Greece. They assisted a lot to create this complete electrical thermal system of the demo site that I will show you later on. Now, they also helped in assisting the smart boiler performance as a thermal storage device. Now, moving on to Asilio. Asilio is a Swedish company also located in Gothenburg, but they also have activities in other places in Sweden. And 3 members of staff were directly involved in that. And also, their main focus was in investigating the potential their thermal storage had connected with the excessive photovoltaic energy, when you have too much energy to absorb, and the flexibility and grid supporting services that this storage device can provide. We have run a simulation of their storage device if it was assuming that it's located in the average Greek hotel. So we try to see if we can also incorporate this technology in the very successful industry of tourism. And this involves all the hotels in Greece. So you will see some of that later on. Now, part of the demo activities for the efficient management of this thermal storage device that can provide flexibility and other ancillary services was transferred to Chalmers test site, and either literally or virtually by interconnecting their test site with Chalmers campus, so that you transfer, instead of real actual power, you transfer data that are reproduced as power on the other side of the site. That's what a virtual demo connection is about in our talk here. So I hope I didn't get you too tired. I will get straight to the point now with the presentations of specific parts. But first, we have a small swap on our program, because our Swedish presenter will have to join us a little bit later on. So now I will ask Dimitris Papadaskolopoulos, an assistant professor in our university, to give us to give us a short presentation about some aspects that are connected with the project, maybe not directly, but some fundamental ideas that you have to understand in order to get a better picture of that. Thank you, Dimitris.
So good afternoon from my side as well. I'm Dimitris. I'm assistant professor in the Power Systems Lab, as mentioned before, here in the University of Patras. So, as Panagis mentioned before, moving to the more, if you like, technical outcomes coming from the project, I would like in the next 15 minutes to provide with an overview of our research, specifically on local electricity, on modeling electricity markets, and how this is related to the concept of demand response and demand flexibility. I will start by briefly mentioning some challenges of energy decarbonization I'm sure you are all aware of. With the large-scale integration of renewables, we need to keep in the system conventional generation to provide all these balancing and ancillary services. And this underutilization means basically less economic efficiency. And on the other hand, we're also planning to massively electrify transport and heat, which increases demand peaks. And this also implies underutilization generation network capacity. So there is a fundamental issue around cost efficiency of low carbon systems. And in this context, different forms of demand flexibility have emerged in the last few years. Panagis has already talked about some of these. You're going to hear more as we move forward this afternoon. But what I would really like to stress is the huge value of this demand flexibility for the emerging low-carbon systems. This is just an example. This is from a report that we did a few years ago with my former group in Imperial College in the UK. It was a report for the UK government where we tried to quantify the overall, if you like, economic value of demand flexibility for the whole electricity chain. So you can see here with different colors, different, if you like, economic benefit streams. Avoided curtailment of renewables, provision of balancing frequency response services, it was mentioned before, avoiding costly network reinforcements, avoiding generation capex, and also meeting carbon targets with less low carbon generation. I think this is pretty important and intriguing because what this says is basically that if we have, as governments and regulators, specific targets for carbon in the future, demand flexibility helps us to meet those by investing in less capacity, less renewable generation capacity. So overall value you can see for the UK system, 3.8 to 8 billion pounds per year, a very huge value, obviously. And this is obviously great news, but the thing is, you know, the real world is not about running a model and quantifying the value, it's how do we actually coordinate demand flexibility in practice. So you need in here two different layers. One is enabling technologies, so control, communication, smart meters, etc. We generally have the technologies required, but I'm going to focus on this presentation on the market level. So in here, it was briefly mentioned before, we are looking at three different, if you like, market layers regarding the integration of demand flexibility. One is bringing demand flexibility to the wholesale market, either directly if we talk about large industrial commercial consumers, or indirectly through aggregators for small consumers. Second is dynamic pricing in the retail market. We're going to talk about this as well. And finally, we could not avoid talking about local electricity markets. Everyone talks about this in the last few years. So energy communities and local electricity markets also central to the Sunset projects that I mentioned before. And the key message I would like to convey in this presentation is that all these three different market approaches to bring demand flexibility into the market and realize its potential are characterized still by significant challenges. And this is where some of our research in our lab is focused. So starting from the wholesale electricity market, basically you have in here two segments. One is the wholesale energy market, and the second one is the ancillary services markets, mainly the balancing market. I'm going to focus on, in this presentation, on the wholesale energy market, because if I was to talk about the balancing market, we would probably need the whole afternoon. As our PhD student Yannis knows very well, there is a huge complexity there. So I'm going to keep it as simple as possible and talk about the wholesale market, the wholesale energy market. So traditionally, the types of offers and bids we had in these markets are what we call simple offers, simple bids, or hourly orders. So this is basically pairs of quantity and price for a specific time period, right? Now, the point is that when you bring demand flexibility into the market, demand flexibility is characterized by what we call time coupling constraints. Their operation cannot be analyzed by looking at individual hours, by individual time periods. For example, in here we have an explanatory model of industrial demand flexibility. So what we can do is either shift their operation in time, what we call the fixed power shifting potential, or we can, to some extent, also control their power at some discrete levels, but still by respecting the overall energy requirements at a specific temporal interval. So you can shift power in time, but you have to, at the end of the day, respect an energy target. So the question is how you really translate these time coupling characteristics to simple offers and bids that are traditionally used in electricity markets. And there are two approaches fundamentally different in here. There is the approach used in the United States, where they use what they call complex offers and bids. So basically the participants provide all their operating parameters to the market operator, and the market operator is the sole responsible for respecting these constraints. In Europe, we have a different approach in order to preserve the privacy of the participant and avoid the complexity of defining many different types of bids. We have what we call block orders, and there is a debate, of course, which of these approaches is better, but we are Europeans, so we believe that the European approach is preferable, and this is where we have focused on. So what are block orders? It's a different type of offers, which basically tries to encapsulate this time coupling. So the simplest one is the profile block order. So you submit a block capturing a number of consecutive time periods, and this block has to be accepted as a whole or not at all by the market operator. So by that way, you can capture time coupling constraints. There are then loop blocks, where basically you submit a buying block and a selling block, and these two, again, have to be accepted simultaneously or no one at all. As you can imagine, this is very useful when you try to bring energy storage into the market. And finally, there is what we call exclusive group, where basically you as a participant, you submit a set of different block orders, and the condition is that the market operator can accept at maximum one of those, right? So at maximum one or none at all. And our position in here is that this last type that we call exclusive group is particularly useful for flexible demand participants, because this can capture alternative demand profiles based on which you operate your loads. So in order to analyze this in a paper we submitted very recently, we developed a stochastic mixed integer linear optimal bidding model in order to compare in here different types of offers, also capturing, of course, the price uncertainty that you may have, because obviously if you are, for example, a large consumer and you want to go to the wholesale market, at the stage of bidding, you don't know what the prices the next day will be. So you have to capture this uncertainty. And what we basically show is that if you have, in a magic way, perfect information about the prices in the next day, right? So you have a deterministic model. In that case, the block orders do not help you at all, because very simply, you would forecast in this perfect way, assumed perfect way, the prices, and then you would bid based on simple hourly orders according to those prices you project. In reality, you have uncertainty, and what we show is that when you have uncertainty, then you need these block orders in order to minimize your costs, and also that you need to go beyond the simplest type, which is, as I said, profile block orders. It is used in most of the European countries these days. You need to go to these more complex types, like the exclusive group, in order to further reduce your costs and make sure that it makes sense for you to participate in the wholesale market. Second stream of work, avoiding going into the wholesale market. Flexible loads interact with an electricity supplier, with an electricity retailer. So how do we motivate flexibility here? By basically providing what we call a set of dynamic prices, either traditional ones, like time of use, the day is divided into 2 or 3 different temporal intervals with different prices, so this provides motivation to shift load accordingly, or more advanced schemes like real-time pricing. So basically the retailer provides you with a forecast of the prices the next day in the wholesale market and gives you motivation to shift your demand according to the real conditions in the wholesale market. This is not science fiction anymore. This is happening in the UK. There are suppliers offering real-time prices as we speak. However, there is an issue with both of those approaches, and this is what we call in the literature demand response concentration effect. So if you have temporal flexibility in some of your loads, electric vehicles, appliances, etc., and if they are automatically controlled and they receive the same prices, you could have this situation. It has happened in practice in a trial project we had in London in the past. So basically, all the loads concentrate their response at the lowest, at the periods with the lowest prices. So you get in there a huge new peak, which could be in some extreme cases even higher than the original one. So by motivating flexibility instead of helping the system, you make it worse. So our work in here has focused on developing different types of what we call smart strategies to avoid this concentration effect. For example, by devising some specific metrics of different loads flexibility and imposing a hard restriction on the flexibility that is actually activated. Developing what we call non-linear pricing schemes, so beyond the traditional linear prices, we devise, for example, quadratic prices or other forms of non-linear prices to avoid this concentration effect, or randomizing, diversifying, if you like, the prices that different loads see in order to avoid having all of them responding with high demand requirements at the same period. And we have analyzed how these different strategies, their effectiveness for different types of flexible loads. And finally, the last part, obviously we could not leave it out since everyone talks about this lately, is local electricity markets. So the idea in here is we don't directly interact with the wholesale market, and neither we require the suppliers to come up with these smart dynamic pricing schemes, but we develop new market structures at the local level, at the community level, if you like. And in here, relevant work has focused on 2 different market functions. Panagis talked about both of those. One is peer-to-peer energy trading. So if I have surplus PV generation, I sell to another consumer in the neighborhood who happens in that time to have high demand requirements. And this has value because, again, as mentioned before, there is a differential between the import price we pay for energy we buy from the grid, which is higher than the export tariff that we are paid when we sell surplus energy back to the grid. And then there is the second market function, which is local flexibility markets. So we aggregate the flexibility within the neighborhood and we sell that flexibility as services, specific services to the TSO or the DSO. So our idea in here was why we don't combine the 2 market functions in order to further increase the potential of energy communities. And we have indeed, this is a work still ongoing. This is a project called Liverpool Energy Exchange. So this has designed local electricity market exactly optimizing peer-to-peer energy trading and flexibility provision in Liverpool, making use of the public buildings of Liverpool City Council. So we basically, in a paper, again, we recently submitted to PSCC, we have quantified the value of this local electricity market design, making exactly use of these 8 public buildings with different portfolios of PV, CHP, and electric vehicles, by comparing a number of scenarios. So if you see what we call in here benchmark is we don't have a local electricity market in place, so every consumer or prosumer interacts in a silo with the electricity supplier. And then we have 3 different scenarios for the LEM, where we make the assumption, and I will briefly talk about that in the last slide, that a common supplier serves all buildings in that community. So what you can see from the results is that with local electricity markets, we indeed combine these benefits mentioned before. First of all, going from the benchmark scenario to LEM1, you can see that we reduce import energy cost because we rely less on buying energy from the electricity supplier. We also have a smaller export revenue because we need this surplus energy to cover exactly the demand requirements. So we also sell less to the retailer. But overall, we have a positive value because the import prices, as mentioned before, are higher than the export prices. And also, we managed to reduce what we call regulated charges. We should not forget this. Our electricity bill for all of us is not only about energy. Energy is just 50 to 60%. The rest is what we call regulated charges. So charges to the ESO, network charges to the DSO, etc. So by this, what we call collective self-consumption, we can reduce these charges as well. And one last point, in the last scenario, what we call LEM3 in here, beyond this collective self-consumption, we retain part of the flexibility in order to sell services to the system operators. In here, we have considered specifically 3 frequency response services that are currently procured by the UK system operator, National Grid. So overall, you can see between 20 and 27% overall reduction of the total electricity costs of the community, which we think is a very significant number. But again, and this is coming to the last slide, again, there are challenges for local electricity markets. Multiple of them. I'm just going to discuss one of them. When we presented these results to the UK regulator, Ofgem, the response was local energy trading is allowed as long as this is facilitated by an electricity supplier. And be careful here, by a common electricity supplier, which means that we need to have one supplier serving and taking care of the billing for all the participating consumers in the energy community. And obviously there is a regulatory issue in here because through some work we published 2 years ago, and we used in here a bi-level optimization model to capture exactly the interaction between the supplier, modeled in the upper level, and the consumers in the lower level who either choose to interact in silos with the supplier or form an energy community. So what we basically showed is that the larger this energy community becomes, the lower are the net revenues for the supplier. So basically in here, the message is that we need to have a supplier to facilitate local electricity markets, but if they do so, their main business model will be disrupted. So how do we bridge that? And going beyond that, there is a requirement that we need to have a common electricity supplier. So if we have a neighborhood where each of us has currently a contract with a different supplier, we need to abandon this freedom and every one of us coming under the umbrella of a common supplier. So these are what I mean to say, there are still regulatory challenges, although the value of local electricity markets is already established and there will be further presentation this afternoon about this. We have to always factor the market and the regulatory framework around this. So this is a summary from my side, and I would be very happy to discuss further with you either now or later during the break. Thanks a lot.
Are there any questions? Any questions now? Okay. We will have a small change of the break that was supposed to be follow after one more presentation, so that we can have it at the end of the presentation, so we can have a whole discussion with the speakers and between us and clear out any questions you may have then. It's better to ask now, since the presenter is in the podium, but if you think about it better and so on, you can make your question later at the end, okay? We will have our refreshment break at the end, and hopefully there will be a lot of discussion and will be triggered from these presentations that will follow. Now, thank you, Dimitris. Thank you. Now, I would like to ask Mr. Vrellis to come for his presentation. Mr. Vrellis is the chief engineer of Maltezos, the company, the Greek company. He will present in Greek, but his slides are in English. So the presentation will be in Greek, but if you cannot understand, you can always revert to the slides and make any questions at the end. I will be used as a translator for that last part. Okay, thank you.
Αυτό μην το χρησιμοποιείτε, γιατί το λέγουν αυτοί από εκεί. Τώρα το πατάτε είτε το mouse είτε το βελάκι. Το βελάκι δεν ξέρει.
Καλησπέρα σε όλους. Είναι χαρά μου που βρίσκομαι εδώ στην Πάτρα, στο Πανεπιστήμιο της Πάτρας, μιας πριν από σχεδόν 40 χρόνια αποφοίτησα από αυτό το πανεπιστήμιο. Θα πω λίγα λόγια. Καταρχάς, μάλλον, η συμμετοχή μας στο συγκεκριμένο πρόγραμμα ήταν μετά από πρωτοβουλία του Πανεπιστήμιου της Πάτρας, του κ. Βοβού. Η εταιρεία μας είναι γνωστή εδώ και 45 περίπου χρόνια κατασκευάζοντας συστήματα για την αξιοποίηση της ηλιακής ενέργειας, θερμικά συστήματα και φροντίζοντας τα συστήματα αυτά να έχουν τη μεγαλύτερη δυνατή απόδοση, να προσαρμόζονται κάθε φορά στις συνθήκες της κατανάλωσης και να εξασφαλίζουν για πολλά χρόνια την απρόσκοπτη παροχή ζεστού νερού στον καταναλωτή. Θα ξεκινήσω μια παρουσίαση του εύρους των συστημάτων της ηλιακής ενέργειας. Ξεκινάμε από τα μικρού μεγέθους συστήματα, τα οποία είναι τα κλασικά θερμοσυφωνικά κυρίως συστήματα που ξέρουμε όλοι, τουλάχιστον στην Ελλάδα και στις μεσογειακές χώρες, προσφέρουν το ζεστό νερό στις κατοικίες. Είναι απλά συστήματα που δεν έχουν την ανάγκη από συστήματα ελέγχου, δεν χρειάζονται αντλίες, λειτουργούν σχεδόν από μόνα τους. Εκμεταλλευόμενα τη θερμοσυφωνική λειτουργία, έτσι, χωρίς κινούμενα μέρη, χωρίς ηλεκτρονικά μέρη, έχουν τη μέγιστη δυνατή απόδοση για μια κλασική μικρή κατοικία. Έχουν όμως αυτά τα πλεονεκτήματα που έχουν, έχουν όμως και κάποια μειονεκτήματα που έχουν να κάνουν με το ότι είναι μόνο για μικρές κατοικίες, για μικρές καταναλώσεις, μέχρι περίπου 300 λίτρα. Έχουν πολλές φορές το ύψος τους, καθώς και η εμφάνισή τους στις ταράτσες των σπιτιών δυσκολεύουν το να εφαρμοστούν από όλους τους καταναλωτές. Για αυτό το λόγο υπάρχουν λύσεις για το θέμα του μεγέθους. Μπορούν να γίνουν συνδυασμοί 2 και 3 συστημάτων, όχι πολύ περισσότερο, γιατί μετά αρχίζει και γίνεται μη λειτουργική η εγκατάσταση. Όπως επίσης υπάρχουν και ειδικές κατασκευές για χαμηλού ύψους συστήματα, για συστήματα που προσαρμόζονται τα κεραμίδια κλπ. Μετά, για μεγαλύτερα συστήματα, είναι τα συστήματα βεβαιασμένης κυκλοφορίας. Τότε όμως, αυτά είναι για συστήματα πάνω από 300-500 λίτρα αποθήκευσης και έχουν τη δυνατότητα να καλύψουν πολλών ειδών διαφορετικών εκτός από την κλασική κατοικία εγκαταστάσεων. Όμως, τα συστήματα αυτά χρειάζονται πλέον αντλία ή αντλίες για να γίνει η κυκλοφορία του υγρού, του θερμικού υγρού. Επίσης χρειάζονται διαφορικούς θερμοστάτες και άλλα συστήματα ελέγχου για να δοθεί ο τρόπος που θα λειτουργήσει, κάποια δοχεία διαστολής κλπ. Βλέπουμε κάποιες σύνθετες τέτοιες εγκαταστάσεις που περιλαμβάνουν και κάποια storage tank, έχουν τη δυνατότητα να δώσουν ταυτόχρονα θέρμανση, συνήθως ενδοδαπέδια ή και άλλου είδους θέρμανση στο χώρο, να θερμάνουν πισίνες, γενικά να δώσουν σε ένα συγκρότημα ίσως κατοικιών ή μια πολύ μεγάλες κατοικίες, να δώσουν ολοκληρωμένες λύσεις. Βλέπουμε κάποιες εγκαταστάσεις εδώ. Να προχωρήσω. Υπάρχουν βέβαια και τα μεγάλα συστήματα που είναι πάνω από 1000 λίτρα, που απλώς γίνονται πιο πολύπλοκες οι εγκαταστάσεις. Βλέπουμε κάποιες εγκαταστάσεις εδώ. Έχουν ιδιαιτερότητες στον τρόπο που σχεδιάζονται, που κατασκευάζονται. Μπορεί να καλύψουν ανάγκες ξενοδοχείων, μικρών και μεγάλων ξενοδοχείων, νοσοκομείων, κολυμβητήρια και λοιπές άλλες εγκαταστάσεις. Βλέπουμε κάποιους σχεδιασμούς, βλέπουμε μια πολύ μεγάλη κατάσταση. Και εδώ ερχόμαστε να δούμε ότι αυτή τη στιγμή, για παράδειγμα, υπάρχει ένα πολύ μεγάλο, μια μεγάλη ποσότητα δυνατότητας αποθήκευσης θερμικής ενέργειας που είναι διασπαρμένο σε όλο τον ελληνικό χώρο και όχι μόνο. Ψάχνοντας να βρούμε ποια είναι αυτή η δυνατότητα, αυτή τη στιγμή υπάρχουν εγκαταστημένοι, ας πούμε, στην Ελλάδα, γύρω στα 5,5 εκατομμύρια τετραγωνικά μέτρα συλλεκτικής επιφάνειας θερμικών ηλιακών. Αντίστοιχα, περίπου 400.000 κυβικά νερού, δυνατότητας αποθήκευσης θερμού νερού. Τι σημαίνει αυτό? Ότι αυτά συνήθως είναι σχεδιασμένα για να λειτουργήσουν σε ένα εύρος θερμικό από 20 έως 60 βαθμούς στην πράξη. Στις δυνατότητες τους όμως είναι να φτάσουν τους 80 βαθμούς. Άρα έχουμε μια αρκετά μεγάλη ικανότητα επιπλέον αποθήκευσης, η οποία μπορεί να αξιοποιηθεί από άλλα συστήματα. Έτσι μπαίνουμε εδώ πέρα στη δυνατότητα αποθήκευσης και ας πούμε για παράδειγμα της επιπλέον ενέργειας που υπάρχει, που προκύπτει από άλλα συστήματα ανανεώσιμων πηγών ενέργειας, φωτοβολταϊκά, ανεμογεννήτριες κλπ. Τα οποία αν θέλουμε να αυξήσουμε τη συμμετοχή τους στη συνολική ηλεκτρική παραγωγή ενός δικτύου, θα πρέπει να έχουμε τη δυνατότητα να τα διοχετεύουμε όταν πρέπει κάπου. Αυτό μας δίνει ότι ότι έχουμε μια δυνατότητα, έχουμε αυτή τη στιγμή μια δυνατότητα αποθήκευσης περίπου 28 μεγαβατόρες τη μέρα σήμερα και μόνο ένα 10% αυτής, αν μπορούσαμε να το εκμεταλλευτούμε για τις άλλες χρήσεις, όπως είναι τα smart boilers, θα μπορούσε να επεκταθεί, να φτάσει στα περίπου έως 3 μεγαβατόρες επιπλέον ενέργειας τη μέρα. Σας ευχαριστώ. Αν υπάρχουν ερωτήσεις, μπορούμε να τις κουβεντιάσουμε ή τώρα ή μετά.
Are there any questions? All right. Thank you for your attention. I think the message that went through is that we have a lot of unused thermal storage capacity at the moment in place in Greece on top of our roofs, and we don't know that. So we should better exploit this thermal storage and make sure that our systems are well interconnected between thermal and electric power, which is something that is not well researched and taken care of. So thank you, Mr. Vrellis, for your presentation. Now, I will go back to the podium. So I will welcome Dr. Dimitrakakis, part of the project from the Greek side. He will talk about the smart boiler concept. He will talk more about the hardware and the electronics. From what I see, most of you are electrical engineering students, so I think you will be very well surprised by what you will see now. So please, Georgios.
Let me check. So, hi everyone. I would like to welcome you to this oral session. I mean also the online attendees that might have entered right now. What you will hear from me is more electrical and electronic engineering, as Dr. Vovos said, and less financial or project management issues. My name, as already introduced by Panagis, is Georgios Dimitrakakis. I'm a physicist, holder of a PhD, and electrical engineer as well, okay? That is a recent degree. So let's start with the presentation. Before starting with the presentation, I would also like to remind you, I will guide you to the Smart Boiler project. Okay, we'll try to explain in a few words what is all the concept about. Yet the Smart Boiler has been only a subsection of a wider project with the acronym SUNSETS, with university partners and industrial partners as well, okay? So what is the smart boiler we're talking about? It's an electronic device. It's an electronic device dedicated to be connected to already existing boiler systems and upgrade them to make them smart. What will be smart? Smart will be that it will offer quality services to the grid, which means voltage regulation through absorption or injection of reactive power and current harmonics mitigation due to the injection of mirror current harmonics from the device. So we will talk a little bit more about it. So what it contains in a couple of words is this smart boiler kit is the power electronics converter, of course, which we will devote some 5 slides about it. And the extra electronic part, which is about the communication, algorithms, and all these microcontrol-based functions. This means, we're talking about communications, it means that where it will be installed, it will need connection to the internet. Okay, either Wi-Fi or LAN connection, or even cellular phone signal. Anyway, that it has to be connected to the outside world. Purpose of the operation. Okay, as I already said, quality services, offering quality services to the grid, but at the same time, it will be used for energy storage. Now, this number Mr. Vrellis mentioned earlier, about these 28 megawatt hours per day in a national scale, is a number I didn't know, and it's quite impressive. Although this system is dedicated, as it is designed by now, is dedicated to microgrids, which are more, let's say, susceptible to voltage fluctuations or harmonic distortion. Still, it's a dream of the team here that someday it will be used for national scale applications, okay? if we make it to release this as a product, okay, with the help of industrial partners, it will be financially meaningful. I have to talk about financial issues in the end a little bit. Financially meaningful for all the parts that are connected to it. I mean, the end customer, which will be the owner of the boiler, the grid operator, and the electricity providers. Everyone will have a profit. The end user will have a profit if you give him some motivation, which is, for example, lower prices when the boiler will be available to the administrator of the system. I have already talked about it. Okay. What you see here is some pictures of residential, let's say, wind turbines. Now, I think this is not the case. Most often we will see photovoltaic roofs in a manner of a distributed generation in the cities. Still, the system is beneficial to the grid, okay, and to the user. And in the far future, it could be also used not only for storage and quality services, but also just for quality services. If you adjust the system, for example, to an oven, there's no energy storage. Yet, since the oven is a highly consuming energy device, it will offer good services, good quality services to the grid. But this could be in the future. Now, as I said before, I will talk about mainly electrical engineering stuff. So this is the, let's say, not a detailed schematic. There is a detailed schematic further on. A schematic of the power converter. The power converter is sort of a step-down topology. It's not a step-down topology, but it looks very much like a buck converter for those who are familiar with power electronics, with a single switching element. This is an advantage. It has only one switching element, which means here an IGBT, chopping the voltage, the incoming voltage. However, there is also a rectifier there, you see, a 4-bridge rectifier, which at the moment we are trying to find ways in a future version of the device to eliminate this rectifier and improve the efficiency of the converter. This may happen with the usage of a second IGBT, okay, a second switching element. We'll see how it will go. At the moment, this is how it works. Rectifying the AC voltage and then chopping it with a PWM scheme, okay, and feeding the resistor. The resistor is the resistor of the boiler. The converter should be connected with a pulse feeding system, which is connected again to the microcontroller and to the administrator of the overall system outside the installation. A more detailed schematic is this one. Here what you can see, okay, you can see again the rectifier. Here is the line voltage, the rectifier, and there is a filter here, okay, an inductor and a capacitor. It's an elementary passive filter. The role of the filter is to cut off any harmonics coming from the switching operation of the IGBT. The IGBT works at 20 kilohertz. At the moment, we have tried several frequencies. 20 kilohertz seems to be an optimum one, not very low, which would require a bigger filter, but not very high. That would lead to more keen noise problems. Here is the control circuit, not all of it, just the end part of it before the gate of the IGBT. Freewheeling diode, and this is the output voltage. What you see here is a picture of a prototype. It's not the latest prototype. The latest prototype is like the one we have outside in the kiosk. And the efficiency is approximately 95%. This is something that we have to take into account, okay, because we're talking about energy storage. What energy storage? We have 5% losses. Okay, it is meant to be used during excess energy production, for example, from renewables, okay? An energy that otherwise would be wasted or had to be exported, okay? or even should be cut off in a generation side management, which means that we should cut off, let's say, 20% of the wind power, which is not something that anyone wants. So this gives a solution to store this energy. I repeat that this is a short-term storage, okay, because it is heat storage with all the disadvantages of heat storage. It cannot stay for long. Heat cannot stay for long, no matter how good the insulation is. Okay, this is where the user, as I will write to you in my last slide, this is where the user, the final user intercepts by choosing a program of daily, let's say, availability of his device. If I come back from work every day at 5 o'clock, I will choose to have my device available from 2 to 5, because then I know I will come back and have a shower. I don't want it to be available late at night, for example, okay? The administrator will decide whether he will operate this smart boiler or not. If there is excess energy, he will activate it. In more detail, some of the issues we faced during prototyping this kit. This is, for example, an improvement, how we achieved an improvement in the efficiency by shifting the filter, the LC filter I showed you earlier, by shifting this on the DC side of the rectifier rather than the AC side. This means directly that the diodes are not now stressed with switching operation, and the improvement in the efficiency was less than 1%. But listen, when you say less than 1%, you had 5% losses, and you can make it 4% losses. This is a huge amount of energy saving, because 1% sounds a little bit small. We will try to make it 1% less. I mean, the loss is 1% less in the near future. And this is the current, what you see here is the current in one of the diodes of the rectifier. Another problem that we faced, among many problems, okay, this is just the highlights. Another problem that we have to resolve was noise issues. Noise issues are related to several things, like the switching operation of the IGBT, which means EMI, electromagnetic interference, okay, radiation to all the circuits around. EMI coming from the environment, from the house, other apparatuses, and anything. We had to shield the wiring. We had to separate high-frequency circuits from the DC supplies of the electronic part. We have to do several tricks to avoid noises like this. The number one thing you do is to connect a snubber parallel to the IGBT, but this is not enough, okay? There are many more things to do about noise suppression when we have to do with sensitive electronic devices, as the electronic control of the converter. Now, reaching the box you can see outside, okay? This is a prototype. It is ready to be certified from an authorized laboratory in Athens right now. Certification means that if it passes the tests of certification, it will conform with the international standards and regulations. These standards and regulations do not guarantee, I repeat, they do not guarantee that the device has high quality or that the device will have high endurance. It will last for 10, 15 years or so. These regulations, if there is compliance with these regulations, they guarantee that the device is safe for the users. It will not ignite, it will not cause a short circuit, and no overheating, okay, that may cause skin burns to the user, and that it does not contain hazardous substances. Okay, this applies to all the electrical and electronic devices in the market right now. Some examples of application here. What you see with the blue curve is the voltage of the grid. With the yellow curve is the current the input current, okay, in the device. You can see that by shifting the operation of the IGBT, okay, properly controlled with a PWM scheme, you can shift the current waveform to lead or lag the voltage. In other words, you can absorb reactive power or inject reactive power. So if you have, for example, the voltage higher than normal, you can absorb reactive power in order to help the voltage drop to its normal value, and the opposite. However, do not forget that in order to, let me show you first the mitigation also of the current harmonics. This is the other operation, okay. That the previous slide was about reactive power. Here you have an example of how the device mitigates the current harmonics in the grid. In a matter of a few seconds, what you see there with these lines, with these curves, is the current harmonics as percentages of the fundamental current component. For example, the third harmonic is, say, how much is that? 18%, okay, and so on. By starting the algorithm of current harmonic mitigation, you can see that in a matter of some tens of seconds, the current harmonics have gone bye-bye. It could be faster, yet there are some limitations in how fast you can make this algorithm. Okay, a few seconds is fairly good to be acceptable. Okay, in a grid where changes happen in a matter of hours, waiting for 10 seconds to achieve the proper result is not that much time. However, in order to activate the reactive power regulation and the current harmonics mitigation, you have to absorb active power, which means that you have to feed the boiler, the resistor, with power. Here is how fast you can change the active power. Okay, if you decide to, for example, double the reactive power injected, you also have to approximately double the active power absorbed. This may happen in a matter of 2-3 minutes, as you can see there. It's quite fast. Okay, it's quite fast. Everything is electronic, everything is automatic, nothing happens manually, and it can be very fast. Now, further than the converter, there is also, on the board, there is also the electronic part. The electronic part is responsible for receiving data, sending data, receiving requirements from the administrator of the smart boiler system, and all this stuff, and in the end control the converter of how to operate, about how to operate. So this board has several things. I mean, this board is not all of it, okay? This here, and measuring, okay, of course, measuring the grid parameters. This may happen at the site of the smart boiler, but it may happen centrally in some, let's say, central point of the grid. There are microcontrollers responsible for sending data, receiving data, making calculations, calculating the harmonics, sending this data, and so on. The administrator of the system could be anywhere, could be based anywhere. At the moment, as Panagis said, we have set up a system where the administrator is in Sweden. So he receives the data from our system here, and he decides of how the smart boiler changes its operation. Okay. I think we are also pressed for time. Now this is the last slide. Concluding, this system, okay, as I said, is financially meaningful for everyone. This system's availability and operation details are determined by, as I have already mentioned so far, user preferences. The final user will decide when he wants his system to be available. Real-time measurements about harmonics and voltage level and the reactive power circulating around the grid. Generation and consumption statistics. We need to know when we have peak energy consumption or peak energy generation, if possible, because as you know, renewables, you cannot predict actually the renewables energy generation. And of course, the administrator server-based algorithms. There are some algorithms that will decide, they will take all this data and decide whether they will energize a group of smart boilers or not. This is from our solar panel on the roof we have in our demo site. Shows some statistics of some consecutive days there. That was it. I could say more, but I was trying to be more fast than I was intended in the beginning. If you have any questions, thank you very much. Thank you very much.
Thank you, Georgios. We have 2 more presentations, and we'll have our concluding discussion at the end. There will be some refreshments too, as was in the this will not be swapped; it will be in place, the refreshments. And first. Okay, so you saw the hardware, you had a look how it more or less works. Of course, behind these quick slides that Georgios presented, endless hours of research, efforts, disappointment, and all this that is kind of involved in all types of research around the world. So let's go a bit higher hierarchically, to see how the smart boilers work as services to the end user and the system operator. So now that you have a good grip, a good understanding of how the electronics work, I will first have a quick presentation of the smart boiler as a concept, how it works and how it supports the system. Its actual capabilities, I will give you numbers of what it can do. And then we'll talk about possible and actual services for the customer, for the consumer that owns the smart boiler. And then we'll talk about more services from the distribution network operator side. And then we'll have some conclusions at the end. First of all, as you understood, the smart boiler provides precise and constant control of active and reactive power during water heating. So it needs to heat water in order to provide services. It's inexpensive, and it provides very quick and fast demand-side management. Actually, Georgios' numbers were a bit outdated. We have tripled or quadrupled the speed of response, both in active and reactive power. And the latest numbers point to that direction, but we haven't taken the snapshots required, and we will not see that at the moment. So it takes less than a second to reach full power, which are new numbers at the moment. And we can extend the operation, as Georgios mentioned well, to any resistive load. It doesn't have to be a boiler. It can be an oven, a furnace, an industrial load that is resistive, and it can be expanded to many domestic uses as well as electronic. As I mentioned before, this package comes at a reasonable price. The range is between 100 and 200 euros, which means many people will consider of making this upgrade if they get the proper motivation from compensation from the grid operator, or from a very flexible pricing system for the power they consume. The fact that it is quite a reasonable investment for someone comes also together hand in hand with a high robustness and reliability. The fact that it has only one switching element means that in case of failure, which is not expected actually, but in case of failure, getting back to work will take you 10 to 20 euros, so it's quite a reliable and cheap construction. So coming to the actual operation, Georgios has mentioned that. As you can see on this slide, which has as I mentioned, the latest numbers, you can have constant reactive power production, as you can see on the slide, on the picture on the left. The middle line is flat, and this is the reactive power fed or consumed from the system, while you change the active power for demand-side management, let's say, quite often, and at exactly the amount of power you want to compensate. That's the difference from the normal boiler. The normal boiler either consumes 2 or 4 kilowatts or no power at all. You can have a control by watt, by the scale of watts. Now, on the right side, on the right slide, you can see the opposite action. You have constant power and constant and regular changes on the reactive power output. So if you are regulating voltage by providing a reactive power compensation, you can have constant power output, and at the same time, you see the voltage and the power factor correction taking place without making absolutely any changes to the amount of power you give to your thermal system. As you can see from the slope of the curves, if you exclude the initiation phase, which is done on purpose slowly, which is takes place the first step change, which is a bit slower than the rest, and this is done intentionally so that we comply with the standards in place. The rest of the changes are almost stepwise. Especially from that distance that you are, they must look completely vertical. But if you look closer, it takes about a second to get from full power to half power or zero power. So we're talking about quite agile system, quite quick, fast, and very, very well operating. Now, going back to the power that it can provide, we will focus on the reactive power capability here. As Georgios has mentioned, you cannot provide any reactive power or harmonic compensation if you don't send power to the water. So this is the reactive power capability curve. As you can see, the more active power you give, which is the vertical axis, the more reactive power you can provide. And the blue lines are the maximum power you can provide. You can see a little change of the slope on the left, on the negative reactive power side, because there is a small capacitor existing on the side of the converter. So it's biased a little bit, a very little bit towards the left, towards working as a capacitor, mostly, because of the presence of this capacitor. Besides that, you can see that the reactive power envelope is quite straight, is quite wide. So with a small amount of active power, you can provide significant amount of reactive power, which can reach about 30% of the active power. If you have 1 kilowatt of active power, you can provide up to 300 VAR reactive power. What does this mean? When you have such a device in place, and when you have this device located in several houses around an energy community, not only you can respond to demand messages, but you can also give a significant support to the grid. If it's a microgrid, you can make this a part of the microsource controller, so not only he generates active and reactive power from the generation side, but he can do same kind of work with the load. And this is a very good negative generator, in other words. So you can make it a part of a microgrid quite easily and gives you a lot of tools to operate. So besides the voltage support, it can provide power factor correction, which practically means that there is a significant reduction of the capacity taken out of the distribution grid. So what you do here, you have the straight effect is you have a reduction of losses on the grid. So you need less power for the rest of the system. You have a more efficient transmission system. So that's a significant service for the distribution system operator. What the local energy community can get of it when it's located in a very close space is they can get improved efficiency of their own energy exchanges. But we're not living 30 years ago we are now, and we have a high penetration of photovoltaics even nowadays. So if you combine it with the power, with the significant power the photovoltaics produce in place, you can create a system that has a high level of efficiency, a high level of flexibility. Because remember, the resistance of the boiler can absorb from 2 to 4 kilowatts, which is a comparable power to the photovoltaics, domestic photovoltaics. And when you have excess power that you don't want to feed back to the system, like in a zero feed-in system, or when the tariff is not good enough, you can self-consume and store it in a thermal system, like the boiler. So it's not only demand-side management, it's also self-consumption and flexibility given to the grid operator at the same time. Dimitris has already mentioned in his presentation of the very positive impact you can get from such loads in demand-side management, so I will not stay and talk more about it. I'll just bring it up here so it will stay with you before you go. And I will go to the last service that it can provide, and that's a service both for the end user, or it can be a service for the nearly zero building or the local grid. And this is the harmonic mitigation. You have seen the waveforms. I will show you a few more to impress you. But at this time, I will show you exactly how it works. As you can see, the smart boiler doesn't have a significant filter in place. The filter in place is for very high frequency harmonics. So first of all, it can compensate its own harmonics by properly adjusting the waveform of the modulation. First of all, it compensates its own harmonics. Besides that, furthermore, when you have harmonics created from neighborhood, for adjacent loads, like you can see on the picture now, it can create, it can mitigate the harmonics on the common feeder. In other words, it can compensate the harmonics the rest of the loads in place of your house produce. So it can improve the quality of power in your own house. But if you have a metering device even further down the grid, like you can see here, for example, you have such a metering device further down the neighborhood, you can compensate harmonics from other adjacent feeders. So in other words, the algorithm doesn't see where the harmonics have to be compensated as long as they are downstream, but it tries to do the best he can to compensate the harmonics at the place you measure them. So if you measure them at your house feeder, it does the job there. If you go further down the grid, it does it there. We have tested that and works. And the amazing thing about the algorithm that we cannot say more at the moment is that it doesn't have anything to do with the type of harmonics, what the harmonics are, in which harmonic order they are. It works from harmonic orders from the third, which is 150 hertz, all the way up to the 13th harmonic, which is the harmonics we are mostly interested in low voltage grids. And it doesn't care where the point of compensation is. But the further down you go, the less you can do, because the power you absorb it becomes less and less significant. But if you replace the resistor of the boiler with a furnace in an industrial area, you can understand how far you can go. Because you absorb too much, you absorb a lot of power, so you can inject a lot of harmonics that will compensate the harmonics down the line. So here you can see what? You can see how the waveform is distorted while it tries to produce reactive power at the same time with active power. And on the right, you can see how this is compensated using the algorithm that I mentioned before. But Georgios has talked a lot about it. I'll just stop and say that it became quite a significant subject at the moment, as more and more sensitive equipment are installed in our houses, in our domestic places, and such currents become more and more significant. Okay. Another thing is that the algorithm doesn't need any kind of information of when and how big the harmonics are that it tries to compensate. So here you can see on our setup, on our laboratory, how we created harmonics using special light bulbs that have this great ability to create harmonics, and some typical domestic appliances like mixers and hoovers that produce a lot of harmonics. And we started the operation of these devices, we stopped them, we restarted it. That's the process you see in the blue circles. And you see that the algorithm doesn't care about the extent of the problem, doesn't care if it's there or not. It just adjusts automatically. So we placed a metering device of harmonics at the supply line, and we created such disturbances in harmonics and to adjust in loads. And you can see how quickly the harmonics are compensated. You see these new peaks every now and then because we flip the switches. We start the devices, we stop them, we start them again, and so on. Now, what was the target? We wanted to bring it down to the standards. And the standards require 5% of THD, which is the total harmonic distortion. And also they require that each and every low-order harmonic is below 5%. It was successful in doing that all, as long as you provided enough power. The currents have to be comparable with the harmonics in order to be compensated, but this makes sense. You cannot ask to produce higher currents than the load can take. So, besides that, some more services that don't come so easily to your head from the smart boiler. With a PhD student, Yannis, we are working on a system that just by the use of one sensor inside the boiler, a thermal sensor, a temperature sensor inside the boiler. That's why the old boilers cannot provide such a service, because they don't have such a temperature sensor. They have a thermostat. They don't have a temperature sensor inside. But if you get a new boiler and it has this capability, you measure the temperature inside, and with Yannis, we're working on models that will, first of all, create the user profile, assess the capability of the boiler to store heat by assessing the losses factors. In other words, it will make a profile of the user and the way he uses hot water, and as a second stage, it will assess your storage capability as a device, as a user, how much energy you can store in reality, and how could you quickly dissipate that stored energy to space from your bad or good insulation. So, first you create a profile. So the smart boiler learns your, the way you use the hot water, and by judging from the tariff system, Dimitris did a good job and mentioned a few tariff systems. Some of them are dynamic, some of them are just use of the day tariffs and so on. But by knowing such information, it can produce enough heat, the smart boiler can produce just enough heat so that you will have the right temperature of water at the right time with the cheapest possible consumption of power. Talking about Greece, this practically translates to using the night tariff. But to more complex systems, this is not such an easy case. So we work also on algorithms that make the best out of this user profile and convert it into a clever demand-side management system that makes the best out for the end user. Now, the next thing we've done, and you probably saw it or you will see it at the kiosk before we dismantle everything at the end of the day, is that we have created an interface that can be added to an open source software. In this case, we have used a software which is called Home Assistant that you can download for free from the web. It's open source, you can do whatever you want in there, so that you can add the smart boiler for free into a smart home automation system. In other words, usually this Home Assistant is used to switch on the lights when it's dark outside automatically, or get information from the alarm so that you know when a burglar is inside and switch on the lights, or adjust the air conditioner or the whatever device you have for heating, depending on the temperature inside the house, or knowing when you are out of the house so it switches off everything. So it's for home automation, for smart homes. If you add this as a device into your system, you can create your own home automation systems. For example, you can, by pressing a button on your mobile, you can say, I'm coming home for a shower. Warm up enough amount of water so that I'm there. And do it with the best tariff, with the best charging scheme place possible. If you tell him when, he can do the best for you. And so the next step is to work on such algorithms that will use such a home automated system and give the best possible for the end user, but also for the system operator. For example, if the system knows that you have a shower I hope you do, every 8 o'clock, every day 8 o'clock in the morning, then this means that he will do the best during the night and the day before for the system operator in terms of reactive power, regulating the voltage in other words. So when the time comes at 8 o'clock, you have your hot water, and you get compensated for this significant service you give to the system operator. Home assistant could be the intermediate agent for that. So that's the other thing that has little thing to do with the electronics, but gives an added value to this device that goes further into the economy rather than the electronic side. And we wanted to test all that. So hopefully we have managed to, thankfully we have managed to use the project as a vehicle to create a demonstration site for such devices. So we created our small local controllable, fully controllable small grid there, where we have one smart boiler, but in the past we had two. One will go for the prototype in sequence. And in parallel with that, we have switchable loads that simulate inductive loads, resistive loads, capacitive loads, combination of such. And these are all done automatically from a central SCADA system that takes information from the current status of the local grid and can also receive commands. We have built our own, Georgios actually did that. We have built our own relay system that receives commands from Simulink that you all know from your studies and translates them to switching operation for the load in place. We have done it for 2 parallel lines, and we have simulated the feeder with different inductor and resistive sizes. So we can simulate long feeding lines on a weak network or short feeding lines in a more robust and closely related network. So coming to the end, why the smart boiler we believe is a good service we should invest further on and do more research and develop even more in all these directions, electronically and financially. First of all, it's plug and play. You just place it there in front of your boiler and it does the work for you. Second, it's web controlled, and this remote operation is translated to messages that can come from a central operator or from your own home assistant or local operation manager. It can be integrated with open source equipment, so it's not closed. You can do whatever you want with it. You can make your own automation, and this will create a community that will be able to add more value to that. It's controlled either centrally or independently from the user, and it can provide, besides the remote control and integration to the home assistant software, a reduction of costs for you. We've calculated that with a normal, we've simulated some cases with a normal boiler that just has a thermostat and switches on and off and keeps the water temperature at a high level. It can create a significant reduction of costs. It can regulate the active and reactive power and can mitigate harmonics. These are all services for both sides, the end user and the system operator, and it can work on the PV self-consumption idea, because we're moving, especially in Greece, we're moving towards a zero feed-in scheme rather than net metering scheme. At the moment, you have a meter that measures how much power you inject into the grid and how much power you consume into the grid, and you do a financial difference. But because the grids are heavily loaded and because there is a significant impact on the operation of the grid because of such a high PV penetration, sooner or later, the systems will have to be converted to zero feed-in. Zero feed-in is you can do whatever you want autonomously, but you will never be allowed to inject power into the grid. You can make it zero, but you cannot inject power into the grid. So when you have such a flexible flexible load and well controlled, you can adjust this operation so that you bring the system down to a zero feed-in system. And the legislation is already there. If you apply for a new photovoltaic system at your house now, there was a checkbox that says, will your system inject power to the grid or not? Now everybody says, yes, it will. But at some point, this box will be erased and your system will be zero feed-in, will be obligatory. Now, besides the services to the operator and to the end user, the system finds applications on different levels and on different countries. So, for example, in Northern Europe, and everybody brings Sweden in his head when he thinks about it, most boilers, electric boilers, are most of the time, if not always, active. They keep the temperature high and the resistance is fully used. So imagine providing service all day round using such a system. Now, if you come to the other part of the world, further down, and you move on to Greece, most households have a solar boiler, and most of you don't know that inside it there is a resistor and there is a normal boiler. And this is underused. This is not used at the moment. You can convert it into a storage device with all these benefits by adding the system. So we found applications that are quite important, and there's benefits for the customers and the DSOs alike. We keep 3 points: voltage control, harmonic mitigations, in other words, power quality. We keep on increased network flexibility and resilience, and we explained why. And we keep the third one, which means it's cheap, translated to robust because of the operation, and it can operate in nearly all non-critical resistive loads. However, I'll give you a secret now. We have already started working on other types of loads, like pumps, for example, or fans that have other operating principles, but still seem to work with such a system, a little bit adjusted, of course. So we also expand the use of the system to provide the same type of services on different type of loads. So thank you for your attention. Thank you very much. I hope I didn't take too much of your time, and I would like to listen to your questions now. Any questions? Everybody's silent. There's one. Great. Thank you. No. I will explain to you how you have a photovoltaic system in your house, and you have a local load in your house. Okay? The smart boiler obviously is a local load in your house. It doesn't matter if the power line goes all the way to the rooftop. It's a load inside your household. So when you don't want your PV to actually inject actually inject current into the grid, power into the grid, you increase virtually, or not virtually, actually increase the local load. And then your meter, the net meter, doesn't spin the other ways. You don't measure generation and consumption separately. That used to be the old tariffing system, where you were feeding power from your photovoltaics to the grid, and there was a meter, and a completely independent system, which was your house, with a traditional meter that was consuming power. Now with the net metering idea, even the zero feed-in metering idea, you have one meter that is at the connection point of your PV and house at the same point. So it measures the sum, the net, okay? On top of that, I have to explain, it's not obvious, that there is a second meter in a net metering device, but this is only for statistical reasons and gives data to the network operator, mostly related to stealing electricity and to know what is going on with the PV production in your place. But this is not actually used for the tariffing system and the money you pay. So you have, in reality, you have one metering device and two lines coming, one coming from the power photovoltaics and one from the household, connected to one bus. And you measure the power beyond that. So if you self-consume this power, the meter sees less PV generation, okay? Okay, thank you very much. Any other question? Now that one started? Okay, okay, thank you. Now, I kept the best for last. Our Swedish friend from Gothenburg is here, David Steen. David is going to present us a part of the work done in Chalmers University, concerted with the local energy communities. I'd like to welcome David on the podium and give him a short description of how the system works here. Yes. My system doesn't work with that. You press the button in front because they also control it from there. So, okay. Yes, thank you, David.
Okay. So super nice to be here. As Panagis said, I'm David Steen. I'm from Chalmers in Sweden. And I will present part of the work that we have done in the project. So this work is mainly done by Mariam Mohiti, a postdoc researcher at our university. And then we have Mohamed Reza, me, and Tuan Lee, that is also part of the group. But to start with the agenda, I will give a short presentation on Chalmers' contribution, what we have done, and then I will focus a bit more on these results from the study that we did on voltage support using reactive power control, where we can use this smart boiler from Panagis and his team. From our perspective, we have also worked very much from the local energy community perspective. So having the electric distribution system where we have solar PV, we may have some battery energy storage, we have some loads, maybe a smart boiler, a thermal energy storage, which is more of a high temperature energy storage from Ancillary, a company in Sweden. We also have the connection to the district heating system. So we're trying to do this multi-energy system where we coordinate both the electricity and the heat system. Basically, we see this as an energy management system. So similar to, as Panagis said, trying to consume electricity when it's good for the system or good for the environment or good for the wallet if it's cheap electricity. In Sweden, we have something that is called hourly electricity prices. So the tariff is changing every hour. Not for all the customers. You can choose if you want to have a fixed price or if you want to have this hourly price. But for those that select the hourly price, then you have, in the morning hours, it might be very expensive, and then it goes down during the day, and then it goes up in the afternoon, and then it's cheap during the night usually again. So it fluctuates with the consumption, more or less. And what we do with the energy management system is then that we make a schedule for the coming day or 24 hours for how we would like to run and optimize the consumption of the building. And then we are using an approach that is called a rolling horizon or looking forward multi-periods simulations, where we rerun the optimization every hour or every 5 minutes to reschedule based on new information that we have, if we have a new forecast, for example. And then we decide the set points for the different devices. And one important aspect that we have been working with to sunset is to the load and PV forecasts. So we have set up a Python script to forecast both the demand in the building, but also the PV generation. So we've had different parameters that we think is important, and we have made something that is called future selection to select which parameters have the highest correlation with the demand or the PV generation, and then use them as input in the machine learning algorithm. We have also collaborated with a company that provides an API for weather data. So they collect historical and future forecast for the weather, so we can easily assess them. And then for the historical data, we have set up an IoT platform with an API connection as well. Then we have linked this platform with the forecasting tool together with the optimization model that we have. In this project, we were using a software that is called GAMS. It's an optimization software, but you can also write the models or the scripts in Python or any other optimization language that you like. So the model is based on a method that is called mixed integer linear programming, which is one way of optimizing and formulating the problem. We have written a function to communicate with the smart boiler here in Patras, so we can read data and send set point when we want to start the boiler, when we want to stop the boiler, or what set points, how much reactive power would we like to have from it. And then at Chalmers, we have the campus area as a test bed. So we have connection to all the solar PV installation. I think it's like 700-800 kilowatt solar PV installed. We have a SHP unit for heat and electricity production. We have some heat pumps and energy storages that we can control and we can get measurements from. And then together with the partner Ancillary, which developed this thermal energy storage, where you have a Stirling engine that produce electricity from high temperature heat that is stored in a phase shifting material. So we have made a simulator, or used a Celsius simulator for that to simulate that we have this this device in the campus as well. So this is a sort of a platform for a virtual demonstration that we have been working on. All right, but let's move on to the reactive power control. So how did we do that? The methodology, or the is called Decentralized Transactive-Based model. So we have two local energy communities with different resources, and each of them tries to, by using this energy management system, we're trying to reduce the operational cost for them. Then we have the DSO, or the distribution system operator, that wants to operate their system securely and within the voltage limits. And then the transactive-based method is functioning that the local energy communities send their schedule for consumption of active and reactive power to the DSO. The DSO uses these values to calculate, okay, will the system be okay, or do we need to do something to keep the voltage within the limits? And if we are out of the limits, then the DSO say that, okay, well, can we buy some reactive power from you? So they put the price for the reactive power, which is fed to the local energy communities, which then re-optimize using the energy management systems again, and see that, okay, well, if this is the price, then I can buy this amount, or then I can sell this amount of reactive power. And the DSO say, okay, now the system is fine, so we don't have any voltage violation, so we stay here. The results from the case study, or the setup of the case study, this is a schematic of the distribution system at the Chalmers campus, where we have divided the system into a normal part, and then we have two local energy communities. So this is part of the 10 kV distribution system. For the first local energy communities, we have solar PVs, we have heat pumps, we have batteries, and a CHP unit. And in the second local energy community, we have solar PV, battery, some flexible loads. We have assumed that we have this smart boiler and also thermal energy storage. And in Sweden, and I think in most countries in Europe, we have a voltage range that is between 95 to 105% of the nominal voltage. And for the normal scheduling of the energy management system for the local energy communities, then we're using these hourly prices from the spot market. And yeah, the simulation study was done for 1 day in April 2021. So it's based on real data from the campus area. Unfortunately, the system is very stable, so there is almost no voltage deviation. So we had to do something. So we were increasing the line length to create some larger voltage dips in the systems. And we also added some inductive load for one of the buses. And then, as I said, this approach is iteratively. So if you look at the schedule or the diagram here, we have the first iteration. We see that there is a need for reactive power. So the DSO set a transactive signal or a price for the reactive power, saying that I want to buy this. And then in the second iteration, they need to increase the price because they need more reactive power to solve the problem. And then in the third, it's increased even further. In the fourth, more. And then on the fifth, we reach a stable point, but we don't really know it, so we need to run it 6 times in order to have a fixed value that doesn't change very much, where the price is quite stable. Yeah, and some results. As I said, we reached it in 6 iterations. And in this case, we provide 10 kilovolt ampere reactive from local energy community 1 and 50 from local energy community 2. And also, as you can see, the prices varies between those two local energy communities as well. And yeah, this is just a figure showing how much we are consuming to reduce the voltage. So we are increasing the consumption of reactive power to stabilize the voltage. And we're using different resources. So in local energy community 1, we're using the solar PVs and the CHP unit, while in local energy community 2, we're mainly using the solar PVs, but also the smart boilers here. And this can also be done with not only to, if we have a problem with to low voltage, we can also have it if we have increased voltage due to the solar PV penetration, for example. So if we have a voltage rise, we need to consume more reactive power, and this is the results from that case. So here we change the topology of the grid again. So we increase the reactive or the capacity of the system to increase the voltage level. And then we are consuming more reactive power in local energy community 1 and local energy community 2 to solve the issue or to be within the limits. And to conclude, we have seen that we can, by using the reactive power, we can alleviate these voltage issues in the system. So it's possible to use the reactive power for that. And this market mechanism makes it possible to sort of set a value of the reactive power. What we found a bit difficult was that how do we actually see how much does it cost to provide the reactive power from the local energy community? Because if we're using your device, it's not very costly to increase the reactive power injection or consumption. But here we were using the apparent power, sort of, or the difference in apparent power with consuming or not consuming reactive power. Yeah, so finally, to what we will do more is to look on how we can use this reactive resources to provide this reactive power, and how we can, if we have a local energy community consisting of a number of houses, how should we distribute the revenue between the different partners in the local energy community? All right. That was what I have to say.
Thank you, David. Now let's storm our guest with questions. Dimitris has one. Yes.
Thanks a lot for the presentation. Two actually questions. One is the results of the specific results. When you presented the price, the reactive power price, in the voltage rise case, was much lower than the voltage drop case. Is there a particular reason for that?
That is a good question.
Excuse me, can we ask Dimitris to repeat the question, because now he has a microphone, can be heard.
Yeah, I was saying that when you presented the two cases, the voltage drop one and the voltage rise one, the resulting price, reactive power price in the voltage rise case, I think it was significantly lower than the voltage drop case, and I was Just wondering if there is a physical reason behind it.
I will check the price here.
Μπορείτε να βάλετε σας παρακαλώ την παρουσίαση την τελευταία πάλι στην οθόνη, γιατί η ερώτηση είναι σχετική με ένα slide. Ευχαριστώ. Ναι, ναι.
Yeah, so for local energy community 1, it's sort of the same, or quite similar.
Yeah.
For local energy community 2, there is a difference. I'm not 100% sure why there was a large difference in the price in this case. It depends both on how much reactive power that is needed, and then on the spot price on this specific hour, because this is how we calculate how the income from the revenue. Yeah.
And the second, if I may, question I would like to ask is, now on the high level, is there in Sweden at least formal market mechanism at the distribution level for distribution ancillary services? Because most countries there is no framework for market products from the DSO, and I think this is related to one of your points and the conclusions that with this mechanism there is no direct interference by the DSO, and I was just wondering what that means, because in national ancillary services, for example, the ESO or the TSO has interference to organize these markets, to receive bids, to clear the market, etc. So how does it work in Sweden right now, and why do you say at the end that this can work without a DSO interfering?
Okay, so to the first question regarding how it works in Sweden, currently there are no markets for reactive power. However, there are markets for flexibility or for active power. And one of the main reasons why we don't have it for reactive power is that there is not that large value of for the voltage support, because the DSO doesn't really have a penalty if they violate these limits, and to be honest, they don't really know if they are violating the limits either, so they don't measure that carefully, and yeah, so that is not an issue. With what we meant with not interfering with the DSO, I think it's, yeah, so basically if you don't, because we have also tested this both with active and reactive power, so the DSO can both buy active power and reactive power. And if they don't have this market, what we see in Sweden is that, for example, the amount of electric vehicle is increasing quite rapidly. And when you have had the vehicle for a month or half a year, you see that I don't need to charge every day. And then they schedule the charging to charge when it's cheap. And if a lot of people do that on the same street, you get a quite high peak during these hours when the electricity price is cheap. So with having some more local markets where you can trade both active and reactive power, then you can avoid this increased peak that you may have otherwise.
Thanks.
Thanks for the question.
Thank you. Is there any other question? Okay, so now I think it's the best time, because we'll have the conclusion. We will be around so we can hear your questions and what kind of ideas you may have to help to assist us with some new ideas. You know, sometimes when there is someone outside the closed loop, he gives the best ideas because he's not focused too much on one specific thing. So we would really like to hear from you, your questions and everything. Also, right outside this door, we have the refreshments. And you're welcome anyway to drink some. So stay for discussion. or on your way out, take any drink, or before you go out, you can take a drink and have it with you. And we'll be here for some minutes. Also, whoever is interested can wait a little bit, and we can demonstrate smart boiler outside before we dismantle the kiosk, because at 7 o'clock we have to be outside of this place. So thank you everybody. Thank you, David.
Panagis, may I ask you a question then first?
Yes, of course.
When we are changing the set point of the boiler to increase and decrease power, have you done any estimation of the efficiency or the losses?
The power we inject into the resistor is 95% efficient.
Yeah.
Now it depends on the thermal system of how much it will absorb into that. We assume it absorbs nearly all of it if it's in the resistor is inside. Is this the question?
Yeah, so but let's say that you have a 3 kilowatt boiler. So the maximum is 3 kilowatt. If you reduce it with the controller to be operating at 500 watt.
Yes. If it is less efficient.
Yeah, or is it the same? Do you have static losses?
The efficiency is not power dependent. It's actually stuck to a value approximately at 95%. Small fluctuations only happen when you increase or decrease the power.
At the dynamic point of operation.
Yes.
Okay.
So it's
95% corresponds to either low power or higher power.
Okay.
so you can consider, but this is of course rough.
Rough.
We're talking about plus minus 0.5, let's say, in magnitude.
Yeah.
But we have taken measurements because it's quite difficult to measure the efficiency of this converter because you have a switch in output, and this is a whole discussion of how you can measure that. And we have used another technique. We actually measure the thermal losses. We measure all thermal output of the device, and then by the hardware description, we go back to the operator's manual and calculate this thermal heat in what wattage, in what power does it correspond. So it's very difficult to directly just put a watt meter at the resistor and see how much watt you inject, how much power you inject into the resistor. We indirectly, not directly measure the thermal losses on the power circuit, taking it out from the input that we can conveniently measure, and this gave us the efficiency that Georgios is mentioning.
Very low power, there is some drop of efficiency, but normally it won't operate at that low power.
You're talking about 100 watts. No.
For values higher than that, it's nearly 95% power dependent.
Okay.
Was this the question?
Yes, it was super good.
It's because of the switch in operation at the output. There is no exact mathematical formulation with the sensoring devices that a laboratory has that we can describe the power output. You have to rely on the losses, if you can measure the losses. And the thermal output is a good way to do a very good approximation of that. So just by touching the cool converter, you are sure that it's efficient.
No
Yes.
losses.
No losses, yes. But we measured how cool it is, and we calculated all the steps of converting the power, and it's 5%. And also, you also used, I'm not positive about that, I'm not 100% sure. You also did another approximation, or am I wrong? Some other way.
One was by simulation and one was by your way with a
Temperature measurement. Yes. So, I think, yes. It doesn't warm up. David, it doesn't warm up. We put our hand. Yes, it doesn't warm up. Thank you, David. Thanks.